So this is a very typical second order system, because from here you can see denominator, the highest degree of S is 2. Basically that's deriving from is a double derivative in time domain. So basically this is a certain type of the second order systems. And we put this one into a feedback unitary feedback loop control. Okay. So for this one, T is the time constant of the linearized system, and K you can visualize a certain controller. Okay, so K here play a role is in the position control. Okay, or equivalent to think about that one, you can visualize K is a certain spring constant to be modulated for the systems. Okay, so now for this case we have C and we have R. Okay, so that is the configurations, and right now I want to give the system design parameters here, the design criteria, and for this system we desire the output performance is something like this, and let me draw it here. And this one, we require this value is equal to 0.245. Okay, and it happened when t equal to 3 seconds. So here we want to find, to determine is the value of the t and k such that the system response will be like this. Basically, here is a designer, you define your criteria, your system dynamics in this way. Then you design the parameters, have the system dynamics will fit into this. Okay. So that means if we would change this number, or if we change this number, then the result will be different. Okay, so from here we can identify this one basically is our MP, and 3 is our TP. So we simply plug into our formula and we see what happens. So from by MP, our formula is exponent minus pi theta. Hopefully this one, right? Can you compare with your lecture notes a couple of minutes ago? Is that right? Good, okay. And now from our requirement, this value must be equal to 245. So from here we can determine is here the only parameter is theta. So therefore we have theta we can determine that is equal to 0.4, about 0.4. Okay. So 0.4, but remember that will fit into the first case if we like to determine second time, third time. Okay. And also by this information TP equal to 3 seconds, and that one's on our formula is pi divided by omega n times 1 minus zeta squared. Okay, so here we can solve for omega n equal to 1.14, and that is in radian per second. Okay, so now we have zeta and we have omega n. Then we have to back calculate the k and t. So again, what is the relation between zeta and omega n to the real case? Basically, is this. From here we can determine, sorry, I kind of jumped around, the transfer functions for this case. So let me call this is GS. Okay, so that is G and 1 plus GS. So this is a transfer function, then we plug in g equal to this one, then we simplify the transfer function is k t s squared plus s plus k. So that is our transfer functions. And compared to our characteristic equations, and that one is t s squared plus s plus k equal to 0. And the zeta and omega n, basically that is the parameters for our standard, the second order system. So basically our standard is s squared plus, let me write it up here, s squared plus 2 zeta omega n s plus omega n squared equal to 0. Okay, so we compare the two cases. Basically here, let me divide it, s squared plus 1 over t s plus k over t equal to 0. So simply we compare the systems. From here you can see basically 2 zeta omega n equal to 1 over t, and then also compare this one, then omega n squared equal to k over t, right? So we simply compare the coefficients of individual one, then basically you should be able to determine the k 1.09 and k equal to 1.42. Okay. So once we have determined this one, then the follow-up maybe I can keep asking is, once you determine T and K, then what is, I would say, continue asking, that's additional questions, is finding the TS, for example, the sampling time, how long you're going to expect when the system is going to settle, which means go to the pretty much this pseudo steady state. And maybe I can keep asking, what is the, say, delay time? Delay time, that is how fast the system will reach the 0.5 value. Okay, that's called the delay time, and or rising time, etc. Okay, and as long as we have this value being calculated, remember all the indices basically are expressed in terms of the two parameters. Okay, so once we have those things, the whole indices can be determined right away. Okay. So that is the simplified, that is the example here. And any questions? If no, then I will go to higher order systems, new sections. So start, we can go to the